Okay. Last of the lecture on the relativity and quantums for classical mechanics. The thing we're going to do today, besides a review, and the review consists of looking again from a slightly different point of view of several things that have to do with these relativity functions of wavelength, period, and all that. And I want to point out a couple of things about the Doppler effect. I call it Doppler jeopardy. And a couple of famous examples of these functions which we looked at last time. I'll do that very quickly. And then some extremes and a plot of these functions versus the row, which is added to the textbook. It just handed to you. The rest of the textbook has that. And then a little bit of the animation of space-time, or space-time, but mainly space-time. That's part of the review. It lets you get a feeling for what these waves are doing as far as metrology. Now the rapidity and the stellar aberration angle are two ways to do this, and we're going to go into that. And this is the Epstein as opposed to Einstein approach to relativity. So that's kind of fun. His book really, he self-published. I mean, it was one of these things where he had a new way to look at it. It was kind of cool, but he only looked at the one side of it and wasn't enough for most teachers. We'll hope we'll do better. Anyway, longitudinal hyperbolic geometry, the relationship between those two is kind of cool. And then we did Occam's razor to get in here, and we'll see Occam's sword today, and that'll help us understand a number of things. We'll go through those fairly quickly, but I want you to see a wave guide, what that has to do. Because that then leads into, and this is the main course today, right here, the derivation of relativistic quantum mechanics. So things, the question is, what's the matter with mass and stuff like that. And then we'll make use of that to do some Compton recoil formula, geometrically. How do you use a ruler and compass to make a Feynman diagram? That's kind of a fun job. And also the physics goes with it. And how Compton recoil is like a rocket velocity formula. We looked at that. That's, I think, something that came out of this, and I've seen it anywhere else. And the second quantization, what does that mean? And finally, relativity in accelerated frames. And the stuff that we do here, you just flip it over and you get a nice example of constant acceleration. And that's already complicated enough to see some of the things that might lead into making all of this into a GR job. So let's get started, because it's a lot of stuff. The first thing I point out is what we did last time with Bob sitting in between two 600 terahertz lasers, and he's moving, so he's redshifted this one down by a factor of 2 and this one up by a factor of 2. This is Alice's 600 terahertz laser. I'm actually being a little artistically prerogative here. This should just say 600 terahertz, because that's what she has as a reading. But I would have to put something there. He's moving, and he's seeing that this is 1200 terahertz, and this is the same with her, 300 terahertz. Now, this arrangement can happen a lot of different ways. The other way is to put both these 600 terahertz and let them just sit there and have him move, or have him stand still and have these two move at him this way, okay? At the speed, this 3/5 speed of light that we've already derived, right? Now both of those are expensive. It costs basically a one United States gross national product to get a pretty good sized rocket ship with a laser on it going at 3/5 the speed of light. That's how much energy we're talking about. It's just huge. Because, you know, 3/4 the speed of light means you're circumnavigating the globe 4 times every second. So it's just a huge amount of speed that we're talking about, okay? So avoid all those expenses. Let them just sit there. and tune it to 1200 like this, and this one to 300, and that's what you see. You haven't spent but the pennies that it takes to get the laser turned on. Okay, so you'll have the wave doing 3/5 the speed of light. Okay, and then it'll be up to you to measure that. Right. So that I wanted to point out just in passing. Now, the idea of going between the space-time and the per space-time, we're going to go into that some more here a little bit in the review and then later on. But remember, all of this is gotten by factoring a wave, basically factoring this sum to make a half sum and a half difference. The half sum down here is the piece standing up, and the half difference is this one. And then when you flip this over by doing the reciprocating of this per space back to space-time, they interchange. This one comes up, and that one goes there. And you remember it started out with these two. This guy right here going infinitely fast, corresponding to a slope of infinity in this graph, and this one not going at all, just standing still, a standing wave, and that corresponded to this one with a slope of 0. So there's a control panel. The idea is to get used to you know, what happens. And we're pushing two keys now to make this thing work. These two right here, these two lasers right here, which we started out in 600 terahertz, both of them. And now we're doing this. And we'll go on and do a little bit more. I want to see some extreme examples of this in the process of the review. Okay, a quick thing about the relativity functions that we make a table of. The picture here, of course, is the space-time with the wave going through and cutting. The blue one is cutting these zeros here that represent the new space axes and represent the phase part of the wave. What we like to call the heartbeat, or the guts of the wave, is going up on these blue line, on that blue line arrow, and there's the blue line that's actually making the zeros. And most of the time, the blue line seems to be located inside the group envelope, pinched there. And of course, that particular zero is the group thing. The new time axis is in the direction of the group. And then the numbers come as these are the functions that we've talked about that have to do with, well, here's the wavelength of the group right here. Okay? Here is the wavelength of the phase. And the idea is the phase is going this way. There's the zero that we don't count. We start with this one and we don't count the next one. We do count the second one after that. And that's right there. So that gives you the lambda phase of 4/3. This is it right there. That's the cosecant zeros, basically. And then on this side of the thing, what we're looking at for the phase, okay, the phase has a period of, this is tau phase, a period of this particular value right there. And that's, this is 0.75, this is 0.8 right there, or 4/5. So that's tau phase, this one right here. And so forth. The group also has a period, you see. The group waves, which are idling along here at 3/5 the speed of light. This is 3 to 5 in slope that we are seeing on the green. Okay? Is this making sense? Just because this is the guy we work with in order to talk about, we'll be doing stuff over again with those quantities. Okay. Now, of course, over in per space time, these quantities are inverted and they serve as coordinates in that neighborhood. So this is just a picture again with the others. And remember, the slope of the phase is more than the speed of light. This one, by the same fraction turned over, is slower than the speed of light, 3/5. Okay. And by the way, when we measure these things to be right about the units, if this is space-time, usually a space is my unit, because I put a C in front of the tau. Remember, we do that. So these are all in units of a half micron, which is the 600 terahertz that Alice's laser is always tuned to. Now, what I want to do is make sure that the algebra and geometry jive, but in particular the geometry. Here we have the pictures of the circle. That's something that we're going to talk more about today, but that's the thing that laid out the thing that started out being the cotangent turned tangents and turned into a hyperbolic sine in the relations. That was our first sort of function to be written down. And then the hyperbolic one then shows up next to the tangent. Okay, so these are all hyperbolic labels, but you can use the circular labels as well. So this is being matched here in this time in space-time. There's a circle, okay. There's another circle we have to talk about. I call that one the Thales circle. We'll see what that means and what it does. And the thing we haven't even really mentioned much of is that this construction produces a hyperbola that's very important for our doing our quantum mechanic. The mechanics of matter come from a hyperbola, and there's just one point out, and there's the other point. That's where the group hyperbola goes, and then the phase has another hyperbola to go with it. So that's coming up right now, very shortly. But at this point, there are the functions that we're interested in. There is a hyperbolic sine of rho going out to there. That will turn out to be a physical quantity of interest. A hyperbolic tangent, we always already know what that means. If this is one unit here, then that's the velocity in units of c. Okay, so we'll be seeing more of this later on. Now, if I recall, we had some sort of simulation on this. I might go ahead and just try that now.
It'll allow you to toggle between the labeling.
That's assuming that this copy and paste that I did is going to actually produce something that this thing recognizes.
Well, late breaking changes right before
There
class.
we go. Okay, so here we have, and this is actually a new diagram, I think. We haven't had it quite like this.
I just tweaked out some of the existing scenarios.
So this lets you, play with this thing and see, what all of the R's on. And he's got 6 trigonometric functions, and you can set lots of different choices here. There's a transition to hyperbolic, where the hyperbolic functions are then put on. And it actually draws the hyperbola just to one. That's really nice to get started. If you're going to use this for teaching later on someday, right, it's hard to find anything better than that. And then, of course, if you want to make it really complicated, there's a heck of a lot of stuff we haven't put on these diagrams, circles and things like that. They'll have physical meaning at some point, but I'll get to those later on. Just doing all makes it so you see the Occam sword, which we're going to talk about today. So you can see, if we do all that at once, I don't think anybody's going to find this very attractive. But you start off with just a few things. Nobody's scared by that, right? Lots of lessons that can be learned just by going through these. Okay, I'm going to hightail it back to the lecture here, and we'll proceed. This is a figure, number 11, of the little text that I handed out. It's been improved so that the actual fractions that go with this are there. Here's the picture of that and the fractions again. This is a quick way to see what it is. Here just a triplet of phase lines going with the zeros, okay, that is whole wavelengths, and that's the thing that was missing in that other figure, is that it was half wavelengths that weren't showing. And so where this one intersects here, okay, that particular point is this thing, and then the green guy, he's intersecting right here. That's the thing associated with the lambda of the group, and this one's the lambda of the phase. And there's the tau of the group, and there's the tau of the phase. So that triplet goes through, intersects, and makes the Minkowski graph, at least a couple of pieces of it. So that, I think, is a nice, simple way to show these quantities here. And of course, there are the coordinate quantities, sine, hyperbolic, and cosh. And I mentioned those were at least one of those was a very important one in just the elementary study. Anyway, the two famous ones are cosh and sec. Sec being the contraction of length. Cosh being used here improperly, really, because the distance here, to me, that looks like a increase in something to do with time, and it indeed is, but that's called a dilation of time, which means a slowing of time. It's not a dilation of the frequency; it's a dilation of the time. So that, in some sense, that's Einstein time dilation. But in order to appreciate it, you have to see how that was read by another observer, and you see it's something that requires observers lined up along your track, synchronized with respect to you, and all this business of clock trick synchronization can be pretty complicated. Anyway, these are the two guys, the most famous for getting relativity started. The person that beats both of them is Henri Poincaré. He already had this stuff. He just didn't know how to publish or get it connected. He just didn't know how to connect. Okay, let's see if there's anything else. I don't think there is. Poor old Herman. I have to mention Herman because you see, 4 years after Einstein had published that paper, he was already trying to get this diagram with the rhombuses because it made sense out of relativity. Most people didn't have any idea what the heck this guy was talking about, and Lorentz was hoping to improve that situation. But there's that sad story, right? You lazy fat dog or something, right? A German, being called a lazy fat dog by somebody with a Polish name, or a Polish sounding name. Anyway, sad. Sad, 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 as Trump says all the time. Anyway, extremes. Here's 4/5. Doesn't hurt to take a quick look at this one, just for the fun of it, because you can always make it. Let's see if I got that. Is that what it's supposed to be doing right now?
There's a little bit of strobing there. Just have to put up with that for.
I just let it go there. There's the picture of it, and if I can go ahead and do one of these guys just to see it. This is a chance for you to just sort of see how pinched these plots get as you start to mess around with the. I guess I could do.
That is actually a coordinate to be mapped with the.
Okay, that's just a mapping coordinate. Anyway, you can see how tight the rhombuses get at 4/5.
Drag from -1 to 1 on the x-axis, and that'll get you the
from
ability to set it on the floor.
Between here and here. Mm-hmm. Yeah, there you go. So you can make it really extensive. You see where Minkowski's plot really is not a very useful object. Anything past about 4/5 is really pretty terrible.
If you release it, it'll update the table.
And there would be a typical value there.
Can you zoom in on this?
And then, well, this one is still on the old settings there.
Okay, all right.
Yeah.
That's an artifact. I apologize.
We'll have chances to look at lots of the tables later on. But anyway, as you roll this thing to 0, of course, it just becomes good old Cartesian coordinates.
Yeah, you use the scroll bar and you'll be able to zoom to your heart's content. I believe this will drag as well if you... you have 3 levels.
I'll go ahead and try it right now. The scroll bar lets me do that.
If you have your
And that really helps.
menu,
You can, then go like this and look at the fine stuff pretty closely in here. So this is a very nice way
right-click
to
on that.
manipulate and teach it.
Right-click to expose the context menu.
And this is the they're the variables that you can set for the thing. And then just click on it, it goes away.
Lorentz transformations
Yeah.
down on the bottom if you want to do it numerically.
Right, yeah. I mean, I've made a program that's similar to this. It's just, but I was just interested in making the 2 coordinates overlay on top of each other.
Yeah.
And this is what you're doing. Yeah.
Yeah.
We use this to
I
print.
used to print
graph.
graphs.
Right. That's what I was
like
going to
this
do
for students and do homework on it.
Yes.
This lets you understand. Just this by itself. You forget the waves. Minkowski had a good idea, and it's just sad that Einstein didn't pick it up. He never published, never used, never graphed, hardly any graphs at all. He's supposed to be known for geometry, but that is not in that sense anyway. Okay.
Change the line width there too, Professor.
This is interesting in the sense that when you looked at those graphs, particularly, and I'll advance this one along here just to show that there isn't much difference over there between the 5/4 and the 4/3, and the same thing down on the lower axis. So the region that we're talking about is 0.6, 3/5 the speed of light. So all of these arrows here are pointing to the values of all of the hyperbolic functions and the exponentials. Here comes e to the minus rho, and here goes e to the plus rho. It doesn't look like an exponential because it's a function of the hyperbolic tangent of rho. That's the group velocity, the usual relativity parameter. Okay, so what's interesting to see is where they cross. That's of mathematical interest at this point, but when you actually play with this thing, you can see little patterns that form when you get these coincidences here, here, and here. And the coincidences are kind of remarkably making a use of the golden ratios that we talked about with respect to an irrational number, right? So you'll see that here, and this is just listing a little bit more detail than you'll find in the textbook, but the textbook has this graph in there. This is a particularly interesting one, though. That's just this, when you're going at the square root of 2 over 2, 0.707, the speed of light, you get just 3 different values in that table. You got crossings at that point that are more or less the same, and they come out to be numbers that are not so golden. Anyway, just for fun, just to see where these functions do to each other. That's cool. And then here I'm making a list of what we know about these functions doing so far. The sine hyperbolic, which later we're going to call that the tangent of sigma, but right now we're just doing hyperbolics. This one is a past-future asymmetry. That's the hard part of relativity, is that the simultaneous line tips according to rho, so that it's a hyperbolic tangent, that is hyperbolic cosine and then hyperbolic sine. Hyperbolic sine is first order in rho, just like the Doppler shifts are first order. In other words, first order relativity, it starts with this one as well as the Doppler. Doppler being first order. This is there, e to the rho. This is e to the minus rho. Remember, everything's, or this table is inverses of each other. Then there's the contraction function right there, the hyperbolic secant, that famous guy. There's the dilation guy there, the hyperbolic cosine, okay? Then there's the inverse asymmetry, which is interesting for some things, okay? And then, of course, the group velocity and the phase velocity. So far, that's the physics of this table of trigonometric functions that we've put together here. Now, I call this Doppler double jeopardy. No, it's Doppler jeopardy. This is poor Bob looking at light coming from Carl millions of miles away. Alice is over here, and everybody's standing still with respect to each other. The idea is to ask, how much velocity does Bob have to go in order that these two light beams, and let's assume they're, covering each other and eventually going to make a wave like we're talking about when they interfere with each other. How much does he have to accelerate so he sees the beams with equal frequency? So obviously this is a hot one, that's a cooler one. It doesn't look that way because it's red, but red is infrared. That's much cooler than green. 600 terahertz versus 300 terahertz. What does he have to do? And what is the frequency that he gets? So right now this light is going to make a Minkowski frame that has some velocity, group velocity. And that's really the answer. I say this is double jeopardy, so we'll play it like Jeopardy. You answer Jeopardy things by a question, right? So the question is, what is the beam group velocity? And what you want to do is get with the beam group velocity, right? Then you will be in the rest frame of that light pair. If you don't have a light pair or more, there's no rest frame. That's the thing about a 1CW. No rest frame. You go running after it and it just disappears on you. You run the other way and you disappear. So there's no place you can rest. But this guy's got a place he can rest, and Bob has to find it. And that's the group velocity, omega group over k group. So that's the difference over 2 divided by the difference over 2 of the k. Difference of frequency over difference of k. But the k's here are 1CWs, so they're related to omega by c. Omega equals ck. So I take the c here, and then I've got 2 omegas. So I've got a difference over a sum. Okay, so that's the basic idea of this. Take the green minus and the green plus, that's 600 minus 300, 600 plus 300, that's 1/3 c. He's going to have to go running away from this thing at 1/3 c. If this were to be a low frequency, you'd have to run away from this one to be a negative value. So this is a nice formula to remember. You see, find your rest frame, right? And of course it'll work in many dimensions if you do a little adjustment, all right? And then I'll ask the question to answer this one. What's the frequency that he is going to find when he gets to home? And that is question, what frequency is a blue shift of the left one and a red shift of this, the WRB, that's what a red shift would be, it's just 1 over blue, okay, of WR, okay? So you say, I got to have the blue shift of the L equal to the red shift of the R, okay? And that implies that you get this, but that's not, you're not done yet. I want to stick that B into there, and when I do there, you get a really beautiful result. It's a geometrical mean, and we've got to play with that. That's one of the things I want to show about this. This is the Thales rectangle that is underlying the half-sum, half-difference geometry. But in any case, in this case, it would be 424 terahertz, roughly. Square root of 180,000. And now I'm being careless here, since I'm doing terahertz here, and I'm doing 2 pi here. Doesn't, you know, you see what it is we're looking for here. Okay, so we've got a difference mean and an arithmetic mean. Those are the two pieces, the group and the phase, okay? And then we've got this multiplicative structure that's the geometrical mean. So that's what we want to play with. The geometrical mean and the relativistic hyperbolas. That's really cool. It goes back, way back, 624 to 543. They count backwards, right, in the before comma era. Used to be they didn't have the E on there. It was before Christ, right? And people got mad at that, and I'm glad they did, because that makes more sense. Okay, now, the basic idea here is really kind of neat. And that is the arithmetic mean of these two is just simply, if I've got these two lined up here, like our 1200 terahertz is here and our measly little infrared 300 terahertz is here, okay? In other words, this is 4 units here of 300 terahertz, and this is just 1 unit here, okay? This is the geometrical construction that leads to the geometrical mean. But first I get the arithmetic mean by putting a compass that bisects the two of them together. That is 4 plus 1 is 5. So I bisect that, strike a complete arc, okay? There's my arithmetic mean. 1 plus 4 over 2, that's 5 halves. And then I look where my center is, and that's the difference mean. That's 4 minus 1 over 2, or 3 halves. 3 to 5, remember that ratio? This is the velocity line, or the phase line, okay? That's your phase vector going off there with a slope of 3/5, okay? But what's cool is if you take your compass again and strike back here, that's the geometrical mean right there. This is this guy's invention, okay? You never make fun of somebody from 600 BCE that's doing geometry.
There's a neat approximation method that uses that.
This is the way you would approximate the thin lens geometry. But also, remember when we had the super ball, it was being pushed into the floor, right? That's when we made an approximation of that. But you first get the exact result, and then you make an approximation based on quadratic versus linear. Okay. So, what you should notice, I think, that's kind of neat about this, is that this geometry is a geometry of the two phasors, the relative phasors, the thing that made the little rectangle that had the circle. One of it making a circle that expanded, but was just going around a circle, of course, relative to the other one. Okay, so you have one phasor, you freeze, and then you have the other one just go around, and that's your interference effect. And when they're equal, you're making basically you have a rectangle right here down to there, and then you have the rest of it down here. Okay, and that is an easy way to show that, first of all, always you get a right angle. You always get a right angle when you subtend the diameter to any point on the circle. So that's the key to solving that thing. But anyway, it's also a key to making the hyperbola that we need. I mean, sure, you can go a circle through there, okay, and you can keep doing that, but each time you do it, you're going to be getting another point on the hyperbola. I can take a compass, literally I can take a compass, one of these guys right here, and I'll take this one because I'm not going to actually draw anything with it. But what I can do is just take a point right here and put it there and tighten the compass at that point, okay, and then swing it up here till it intersects the line that is vertical on a piece of graph paper right there, and I'll be on the hyperbola. So you can really very quickly, you know, just go doot, doot, you see, and make dot, 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 the mass shell. That's what it's going to be, the mass shell for a particle, the dispersion function for matter, or dispersion function for a waveguide. Those are two things we're going to talk about in detail. Okay, so this is, you know, we're going way back here in the ancient things. I'm going to go ahead and give it a try, see if it, yes, there we go. So here I can just, you know, keep making a bigger circle. I don't need a compass when the computer will produce all the stuff I want. But there's a complete graph paper that's going with it. All the things are turned on for this one right now. But there you see the little rectangle getting very skinny, and the Minkowski graph getting thing. And there's a starting point right there. And it's also nice when we get a chance, we usually show the visual limits around 600 terahertz, just for people to think. Now remember that in per space time, red's going to be up, because that's talking about large wavelengths and large periods, right? This is talking about frequency and the wave number. Okay, I think that's all we need. Let's go back to the main thing. All right, now these are animations you could have a lot of fun with, because here you learn to use the graph and show the scenarios for various things. I think, except for, let's see if I've got this main lighthouses space thing. I maybe will do one of these. Let's just take this one for the sake of it, because this is something we're going to talk about also, and that was if the emitter is moving and it's making spherical waves, which are much more complicated than the ones we're working with, spherical pulse waves in this case, and these two pulse waves of these two pairs are being used as timers to set the other one off. That's a good scenario to, you know, give students. It's the only one I had for a long time before we discovered this wave stuff. There's the Minkowski graph showing the main lighthouse, and then the north lighthouse. This one would be off of the screen. So this is a two space dimension, one time dimension set of pictures going here. Anyway, it's fun to put a lot of waves on this thing and let it run, and it's quite spectacular. So I hold that to you as a thing to play with when you get some time during the holidays, presumably. Okay. The rapidity and the other kind of angle. This is comparing longitudinal parameter, the rho, the rapidity, the logarithm of the Doppler shift, to this parameter that astronomers knew about probably much more than rapidity. And that's just a stellar aberration. And our motion in the orbit of the Earth around the Sun is sufficient to get a measurable stellar aberration for light that's in the upper part of the northern hemisphere, but it works for other things as well. But the basic idea is that if something has a vertical motion, some light from a star has a vertical k-vector okay, and the vertical speed of light, the vertical velocity of light, and you start moving, in order to catch that light as it comes down, you're going to have to be moving this way so that it stays inside the tube of the telescope. That is, follows that angle. That is where the star is going to appear to be if you're moving really fast. That's a big angle. Okay? These two parameters have the beauty that each of them, this one in radians and this one in whatever you want to call the area of a hyperbola that we've staked out in a sector, they all, both for low speeds, are the relativity parameter to very good approximation. They are both u over c at first. One of them's a little faster than the other, and we'll see that. And then finally, they're completely different. By this time, there's no comparison of the thing that we've been using, which is a rapidity, and the hyperbolic tangent of that is the velocity. Here, the hyperbolic tangent of rho, the u, is the sine of this thing. Now, you remember, the sine and the tangent go together as country and city cousins, right? So this is the first example of that. Okay. Now, this guy came at this in a completely different way. He wanted a way to teach us students at City College, San Francisco, relativity. So he self-published this book, which has the following basic ideas. But in any case, where it shows up in our diagrams is right here. That is the angle right there to the star that he's talking about. That's the angle sigma that goes with a particular value of the rho that's set right here. And that's the one that makes 3, 4, 5 triangles. So that's 3/5 the speed of light along that line gives you a stellar aberration in this direction. So already by 3/5 the speed of light, the stellar aberration angle exceeds the angle that you would have for the tangent, arc tangent of 3/5. Okay? This is all 3/5 speed of light stuff that we've got here. So, what Epstein did, and I've just put it all together here so that it makes sense and also makes connection with the rest of the world, and that was the thing he lacked, and that's why it didn't catch on. And I had him visit here, and he didn't seem interested in the rest of the world. So, okay, that's fine. And no, you know, I'll have to be the one that advertises his thing. In fact, I've had advertising for the book. You can still buy it at a number of places, including in Germany, it turns out. But anyway, look at what happens here. The Einstein time dilation, the thing is hyperbolic cosine. Well, cosine goes with secant, we know that. Okay, so that's fine. That takes care of this, and that's what you want. You want the secant, that's the inverse, if you've already set these other ones. Okay, and then Lorentz contraction. That's the one that has the hyperbolic secant. Well, it's the cosine. Okay, the actual Lorentz length contraction. That's this thing right here, right? That's exactly what the doctor ordered. Okay, here's the simultaneity, hyperbolic sine, right? Okay, well it goes with the cosine. Okay, so it's this thing right here. Okay, so there's your Lorentz contraction. There's your simultaneity. You see, this guy down here is out of whack by this guy by that much. And here's how he works this. The way he works this, and this is the key to this, is to, I guess I don't have that written here, but he just takes the proper time equation, that's this thing, c tau here, and he turns it into a Pythagorean relationship. So what he's doing is he's saying, I'm going to have my CT be here, and this be the proper time. And then I can, you know, that's what that is. But then I can have a Pythagorean set, a rectilinear set. And the idea is that everything, the way he says it is, everything's going the speed of light in a space like this, an ordinary coordinate this way and the proper time this way. And everything is going, something that's standing still, okay, it just goes this way. So after a certain amount of time, the thing is here, and meantime this thing right here is moving, this point is going on that, I don't know what you want to call it, indicator of the coordinate time. So what you see then is this C tau right here is the actual proper time that would be read by somebody riding on that particular point. Well, it's kind of a neat thing. This is the oh yes, here it is. The trick is to turn the hyperbolic form like that into a circular form. So C tau plus x, okay, and it puts the prime on there to indicate that it's a coordinate. C tau and x right here make the time, the coordinate time that you would get by the normal relativistic analysis. And the idea that we're all just cruising through this proper time thing at the speed of light. We can't do anything about that. So the question is, how do you exceed the speed of light or catch the speed of light? Is not a question anymore. That he makes a big point of that. You are going to speed of light. That's all you're ever going to do. You see. It has connections to some of the quantum optics, I think, as well. Okay, well, back to this, but now with the ability to look at the stellar aberration line. That is an important line because that is going to be the K vector in a wave mode, waveguide. Okay? And this little s here stands for stellar or solar or sigma. We're using the Greek sigma to indicate that angle, the stellar angle, right there. But what you get is a little stairway here, where this thing goes up to the ordinary relativity line, comes back to the stellar aberration line, goes up again, comes back, okay, and then goes up. That makes what I call the sword, Occam's sword. This is a really nice pattern recognition tool for all kinds of situations that involve medium values of the speed of light, or speed of something, medium fractions of that. So I mentioned that. I'm going to go ahead on this computer here so that we can do some of the things that are coming up here. There, of course, are the actual values of 12 wave parameters, but I think I can do a good look here just to see this thing all together. This is not too different from what we just looked at, except it doesn't have the Minkowski turned on, but you can see the angles that we've talked about already, and I'll go ahead on this one. I think this is the one that has that. This one also has table to go with it. Let the thing settle down there a minute. Okay. So this is expanded in the sense that it's showing what we're going to talk about next, or next after the waveguide stuff, that has to do with Lagrange Hamiltonians and all of that. So these functions that we're working with are all going to be assigned to the physical variables of mechanics. Okay, I'll bang out of that one, and we'll come back on this one as well. Anything else I need to say? I think that's it. Let's just take a look at this thing. This is another try at making a more compact thing. It's just based on circles. It doesn't help, I think, that much. In any case, here is an actual waveguide for which we have animation as well. This is showing the phase wave go through there, but there's a group. The two of them are going together. Basically, the group is associated with part of the wave that has to bounce off of the thing. In other words, the part that's associated with the K vector. So this is the Occam's sword, opened up fairly far. We're talking about a speed here that's fairly high. Somewhere I had written it, but it's, yes, here it is. This is with the group being c over 2 and the phase being 2c. Okay, so this is 1/2 the speed of light. It's just a little bit slower than what we've been working with, which is 3/5. But the Occam's sword, which you see over there on the right-hand side of the static screen, is the thing that opens up, and we'll see plenty of animations of that later on. Anyway, the notation here is that the E phase wave zeros are the red for this this mode. The mode makes a lump here, and then a trough here, and then a lump here, and a trough here, and that thing goes through at the phase velocity, which is always faster than light in a waveguide. Okay, and then the group velocity corresponds to whatever it is that is actually following a signal. If you put a signal on one of those, a little pulse on something that causes a bump in the phase, that this is what it has to do. It has to bounce off the walls. This waveguide is fairly close. This one right here is fairly close to the cutoff. The cutoff comes right at the top here, where you would have the wave just bouncing back and forth. This is zero group velocity. Okay, it isn't going anywhere. And the phase, which is now a very long wavelength, is really going fast. So again, the two are inverse to each other. All of the kind of stuff that happened with our Alice and Carla waves are happening in a different way with this one. That's a 2 + 1 dimensional space-time.
The next slide has the animations.
See if they're the two of them together. And and here is a simulation, so you can get some feeling for that. This is a 60-degree one, which is the top. Let's see if we can get that to work here. Yeah. So there's the phase stuff, and there's the group stuff. The group velocity now is just 0.8 of the, or close to 0.9 of the speed of light. So it's going along there. And the phase velocity is 1.15. Product of those two comes out to 1. Okay. So here is the diagram of the very simplified diagram of the Occam sword. Okay. And the sigma value for this, the stellar aberration angle, okay, is measured in the same way that we had before. It's the K vector. K vector tipped over. So the analogy is perfect. There's not an approximation. It's a beautiful geometry. Okay. I'm going to pause this and continue. That's something that's worth playing with to get a feeling for really what's the simplest possible wave guide phenomena.
The bottom diagram is a control, so you can approach cutoff and see what your front pinches off on the edge.
Yeah, as you bring this thing up higher and higher and higher, of course that corresponds to being closer and closer to zero group velocity, back to the standing wave. And finally you make a standing wave. Now what's neat is when you're in that neighborhood, that's equivalent to having Carla and Alice shining a laser from top and bottom. You see, you just have them making a standing wave this way, right? And then you let them tip their two beams a little bit to get a wave moving this way, like this one. And then finally, get those K vectors, lined up, with the corridor more and more, you see, so that you have the nice short wavelength inside here, and the K vector, down, going where it should go. So the idea of all of this is that, and this is the thing, there's the hyperbola, there's the actual dispersion function for the guide right there, there's the hyperbola that has it's a high-pass filter is what they call it. No frequency below there is going to do anything but make an evanescent wave at the front end of the waveguide. Won't propagate. But right at that point, you won't propagate either. You'll have the extreme case of this thing up and down, and that corresponds to waves meeting almost head-on. And then as you swing them like this, you get more and more like this, and then this, and then find for a waveguide that really works. This is a waveguide in an area that doesn't make much sense to be, except for the interest in the non-behavior of that. Okay, now spherical waves also are of interest, and there's a section on this, not in this text, but in the other one, that's worthwhile looking at. And this is interesting just for the fact that this geometry of Occam's sword also occurs in space and space. It doesn't have to be space-time or per space per time, and it can also be per space per time. All of this geometry carries over to virtually any situation. Now this is really space and space, and what you're looking at there are those spherical waves that we were seeing from the lighthouse, only lots of them, and I'm approaching C right here. And what's interesting now is there's an ellipse in there that's keeping track of a couple of things, but mainly the focus of the ellipse is right there, and that's just well, it's this tiny little distance right there away from each of the wavefronts. Each of the wavefronts here are very, very close, so this is a very Doppler shifted wave, and we're talking about very high speed right now. In any case, there's the Occam's razor there, and there's the stellar aberration ray that is responsible for each of these are perpendicular to that as you change the speeds here. So this is there's something you can adjust it with. The so all that geometry is here in this case space and space, and you can also plot it, and that's the next thing. I think I can show you pretty quickly here. If we go back, it can also be shown in per space per time, in which case then you actually see something with color. This is a spectral diagram that is also being made by that. TC has really worked hard to make these things. So you start out with two lasers that are green.
Oh, that's cool.
Okay, there's, you know, as close as we can get to 600 terahertz without faking it too much. And then as you work your way this way, you see it's the synchrotron effect.
Oh, and that goes black. So you can't even see the wave
Yeah,
on the left there.
very soon your light is just
the other
composed
direction as well.
of
Oh,
light that's invisible, either infrared or UV.
ultraviolet, yeah.
And UV is on the side that I am on right now.
That's a really neat animation.
That's one thing the sci-fi flicks get wrong. They usually show it all getting bright up front, but
Eventually
you get a black dot up there as well.
Yeah.
Good luck
So
seeing that
this
comet
is,
you're gonna hit.
yeah, if you want to study the synchrotron relativity, it'd be hard to do better than this particular demonstration here. But all of that, well, the ellipse and all of the stellar aberration rays and the Occam sword is being shown right at the moment here, but you can see where it would be. There it is right there. You can draw it there, you can draw it around the center. So that's another thing to study. That this geometrical way of looking at things has given us. Okay, well, the main course is about to come up here, and that's what I want to show you, and that is the derivation of quantum mechanics. So the idea is to examine one of these first, one of these relativity quantities, and the one that I've picked out here is the one that has to do with the heartbeat of the waves we've been playing with. And that's the phase. And the phase has a frequency and it has a wave vector. So we're going to take a look at those two. The Kosh and the Sinch is what we're playing with now. Okay, all of what we know in the world is due to those two fellows. And at low speeds, at low rho, this Kosh very nicely comes out to be a quadratic function plus a constant. And this one just comes out to be a linear function. So we're talking about the U much less than C. Then that's a very good approximation, because C is that thing that's 3 times 10 to the 8th in MKS units. And while we're at it, we might as well mention that the rho is now U over C. It's hyperbolic tangent. As I said before, at low rho, it's just U over C. It's a good approximation. Okay, so those are the three that we're going to play with. But particularly, let's start with this one. So what we do is we say, okay, if that's the case, if this thing right here is linear, I can, and it's equal to this, I could rewrite this rho here as UC squared. Okay, so I get a U squared over C squared, and then the B was already here in a half. So there's a new phase as a constant, same constant times U squared. And while I'm at it, good old K phase is keeping track of me the same way. Two constants that are the same. Whoa! I've seen this before, says Galileo. Well, certainly Newton has seen this before. Something that's 1/2 something V squared, or U squared, okay, and then something that's that same something times U, right? Hey man, this is energy, this is momentum. Except for this dumb B here, but that doesn't bother me, because you can put any constant you want on kinetic energy and the calculation will be the same. It's a difference in that that's going to count in any sort of collision or whatever. Okay? So, we're saying this resembles what we've seen before. Okay? With an M, that's that silly constant there. It's the same M for both. Okay? Now, the units aren't right. The B's have frequency units, right? Hertz. These are hertz, right? Okay, and by putting the C on this one, it's the same. Okay, we're talking about hertz units. And we've got this velocity C. We've got U squared here, so fine. This is frequency, but I still need to change that frequency. If I'm going to call this energy, I've got to put something on there to make it so it has at least the units of energy. And when I do that, okay, this is what you have to match the units in order to make it good for a physicist. So I'll go ahead here and I'll put an H on everything here, and I might as well go ahead and do it here too, and it turns out that's what the doctor ordered. This one's giving me, with a U squared, this cancels the C squared, so that gives me frequency, but this one has an extra in the numerator velocity, so this one has the units of momentum. Okay, that's pretty easy. And writing this thing fully out like that, okay, is perfectly all right. But here is what has happened. If this is true, then HB is our famous number. Okay? That's pretty wild. A rescaled B, and what's B stand for? B for bottom of hyperbola. Right? But it's actually HB is bottom of hyperbola. Okay? Now you have to ask, this could just be a cheap trick with lucky coincidence. Okay? The test is to replace the approximate values that we've got for these with the ones in the table. Okay? Let's try the exact new phase first. Let's just do this one first. Okay? So we stick that in there and we get a hyperbolic cosine. Okay? You get this. All right? And I say, okay, yeah. But wait a minute, the hyperbolic cosine is this thing. We've just proved two things. Planck's axiom and Einstein's energy. We're done. With the energy side. We still don't have momentum yet. Okay, but we've got the energy. Now we can argue, and that's the thing that Planck really worried about, is the energetics and the formulas that weren't involving the frequency in a quadratic way. I'll get to that in a minute here, but at least these are exactly what the doctor ordered. Now you've got to realize Planck did this stuff as a hypothesis that he really hated for quite a few years because he thought he'd made a horrible mistake, really felt depressed, okay? And the thing that needs to be replaced here is this H with H times an integer. Okay? And this will match then with the energy density of what he was talking about, a box of light, which is what we're talking about, right? So E squared epsilon 0 is going to be Hn times new phase. So that H should be replaced with an Hn. And that works fine because, well, we'll get into a little bit more of the electromagnetism possibly in a minute here, but that's what is going on here. Now it also motivates the whole idea of the particle normalization. In other words, it looks like the stuff that guys in quantum mechanics do with their size is the same as what we're doing with E. Almost, except for the epsilon 0. Okay? So wave function has, this is called the quantum field constant. That makes it into a quantum mechanical thing. Okay? Now, the Pauli challenge site has some more stuff on quantized amplitude that I'm just putting down here. But there's still this big worry. Is not an oscillator energy quadratic in the frequency? This is what one of the things that Planck seemed totally to be at a loss, that he'd made some horrible mistake, that how can I ever get my energy back the way it was in my harmonic oscillator class, right? And the deal there involves this thing. But the resolution, and I call it a dirty secret, is that all of these things are frequencies. So in fact it is a quadratic frequency. It's just that this frequency is the phase, and the phase is doing all that crazy stuff going faster than light, and every once in a while popping up and giving you a measurement. And so this is number of counts per second. That's the quantitative frequency. The qualitative frequency is new. That gives you the color of what it was you destroyed with that count. So it is quadratic in the frequencies. This quadratic function in energy is indeed quadratic in phase-based frequencies, I should say, and probably a better way to say that. So that's what it works out to finally, and people don't worry about that. Planck breathed a sigh of relief on doing that. Next topic, and this is 21 now, not starting in 1900, now 21 years later after Planck, or 16 years later after Einstein redid some of this stuff of Planck and got relativity going, we do this. And look what happens. This K phase right here is a hyperbolic sign. And the hyperbolic sign is, and it takes just a little bit of manipulation of the old-fashioned notation to produce the well-known formula for momentum. Now the c squared disappears. I put a c on p to match a c on k in order to write this thing in a way that we can graph it in a square graph. So that's the momentum. H bar kappa phase p equal mu 1 over the 1 minus u squared over c squared. So that's 1921. Took quite a while, 16 years, to go between these two. Here, of course, we don't take that long with 20/20 hindsight. All right. Okay. So that's pretty neat to be able to. I mean, we really show this is an expensive trick. Natural wave conspiracy, if you will. The way that, you know, and how many axioms do we have? We just have Evenson's axiom, which we've kind of proved. So the only one we have is time reversal. That's all we're assuming. And that in the geometry of waves. Now if you actually go ahead and take these things, this is the resting mass and the energy relationship. If you take this momentum one and blow it up, cosh squared, and you can write that as 1 plus sinh squared, and very soon you have another more common expression for momentum squared with mass, the mc squared as an energy. Then you get the parabola that we've had all along here, and there's the bottom of the parabola right there, mc squared. The thing that's being covered up here is the other side. You see, we've got the phase side here, we've got two group sides, and we've got another phase side that's down here, the negative energy guys. So that's the part of it that is really mysterious to me still. And that's something that work needs to be done. There's being exposed a little bit. But in the meantime, be aware that what we do with Schrodinger is throw away the mc squared and just look at this thing in this region. That means you scale the heck out of it, because what energy you're in is a couple of electron volts, and you're talking about, just for an electron, millions of electron volts. All right? So you have to scale by 1,000,000 this very flat region here. And when you do that, you get a nice parabola, which is the ordinary Bohr-Schrodinger parabolic dispersion function that you put into every Schrodinger equation. So that is the thing that everybody works with now. And no one worries about the fact that you threw away this huge number, mc squared. Because remember, it's energy, it's frequency. Frequency is the same as energy in the sense that you're only interested in the differences. The actual measurement of a phase frequency is, well, some would say for quantum mechanics impossible, but it's very difficult for any sort of oscillator. So this is a summary of how all of those constants that have those nice geometrical properties for relativity now have, well, that's what we have to show, is that we've got the Lagrangian and the Hamiltonian and the Broglie wavelength and momentum tied up in these variables of hyperbolic sine, hyperbolic secant, hyperbolic cosine, hyperbolic cosecant are all part of this geometry, certainly part of the physics too. But before we do that, I want to talk about what's the matter with mass. What is mass really coming out to be here? And this fellow says, I matter. And does. You can't argue with that fellow. So what we're going to try to do is show a couple of different ways to look at mass, and it turns out there are at least three kinds. The kind that you're used to that has heft or a punch or an inertia or gravitational attraction. That's a fourth kind. We're not going to get into that one. That's still something of an issue. But momentum mass is what you have learned if you have studied relativity the ordinary way. And the way I'm going to attack it here is define it by the ratio P over U. Now P is mv or mu, and I divide the U out, I've got m. Okay, so I'm going to define it that way, but I'm going to use the new definition of momentum that we've come up with here using kappa phase. And then U will be the group velocity, okay, which is the hyperbolic tangent, okay. So I'm going to have a hyperbolic sine over a hyperbolic tangent. That's what the momentum Galilean mass, I might call it, Galileo's mass, is this one, okay? Well, that's what people say all the time in relativity books, is that momentum just means the mass gets heavier by the dilation of the, well, it's a hyperbolic cosine for us, okay? And as you go to high speeds, this one becomes exponential, so it just disappears. This one, as you go to low speeds, is the original rest mass. So rest mass and momentum mass, at least at that speed, low speeds, are the same. And Newton would be happy to hear that. And he would be very sad or angry to see it exponentiating like that. But there's another one. There's Newton's mass. Okay? The force divided by acceleration, F equal ma by a classical Newtonian. The F divided by, that's a mass, okay? But now we're going to use the modern P and the modern U, the group theoretical, I'm sorry, the group wave, group velocity wave, envelope wave, and then the P would be the new P that we've just come up with here. So that takes a little bit of algebra to do that. I'm going to be doing a dP now, okay, of that is the hyperbolic cosine, takes the sine into a hyperbolic cosine. Okay, so that for that differential. And this is to the change, the velocity, the d of the hyperbolic tangent is the secant, hyperbolic secant squared. So it's those two things that we're going to be ratioing here instead of those two. Okay? Well, this gives me cosh cubed. This one just gave me a lousy cosh, but I get a cosh cubed out of this one. This is a weird mass. Turns out it's the effective mass. Now the limiting cases, once again, if you're slow speed, it's the rest mass. So, you know, at low speeds it looks like there's only one kind of mass. But as you get to higher speeds, there are three kinds. And it depends on what the physics is. What are you doing? How are you measuring that thing? That's what you're going to feel. Now there's a more common derivation of this, based just on going for the group velocity right away. I got dP du, and that means dk with an h bar, dv group. Okay, now v group is d omega dk, and that's a dk, ddk, because I bring that down off the ceiling here and put it on the floor. And I got a double derivative here with an h bar in it. That's really weird, but that is the classic quantum formula for what's called effective mass. The mass that's due to inertia. The inertial mass as opposed to the punch mass that Galileo would give. Very different at high speeds. Okay, really strange. Okay, this is a general wave formula for the effective mass. We got to talk about some of the examples of this, but this one is to accompany the group velocity, which is d omega dk. This one is involving the double derivative of omega dk, but in the denominator. And it's a curvature, basically. As you get more curved, as you come down here, the effective mass decreases to the limit of the rest mass. But as you go up, the circles get bigger and bigger that are containing the radius of curvature gets bigger and bigger until finally, way up there, the radius of curvature goes to infinity, and you're getting something with an infinite effective mass. Well, that's what a photon is. A photon is the thing is by Evensson's axiom has to toe the line, march in lockstep with all the other little photons at c, right? You just can't change it. That's infinite effective mass. So a photon has zero rest mass, but it has infinite effective mass. This is an example of that. Rest mass is that, effective mass is that. The momentum mass depends on the frequency. So if Newton complains about corpuscles having fits, that means going crazy. Well, this would be an evidence of some pretty crazy stuff. Triple schizophrenia. Essentially, the photon can have any mass it wants from 0 to infinity. Now, what are the actual numbers? H nu over c for our 600 terahertz light. Okay, talking about 10 minus 36 kilograms. That's not anything very heavy. So we're not way above. What we're talking about is if I have to accelerate a cavity, that's what I'm going to be dealing with. In addition to the huge mass that the cavity has, all the mounts and everything. So we'll do a quick rundown here very quickly because I want to get to some other stuff. But the Lagrangian is tied up with the phase. So if you have a phase, it's kx minus omega t, and I go differentiate that with respect to t, I get a velocity right here next to a momentum, and then I have this thing right here. So this is the energy, Planck energy. Here's de Broglie momentum, and here's a velocity, at least for all purposes that we have to do right here. As long as I replace the velocities with the right things. This one gets replaced with a hyperbolic sine, that one with a hyperbolic cosine. Okay. So what I'm getting here is the relationship between a Lagrangian and total energy, which is the Hamiltonian, and we'll end up with exactly Poincaré's relationship, and that's the Legendre transformation right there, which we talked about that before. Okay. Now we're going to use group velocity for u. That's the only fair thing. Hyperbolic tangent. Okay. So I'm going to be putting the sine in for momentum and the hyperbolic tangent in for the velocity, and then the Hamiltonian that comes with that. Okay, this is the energy with our hyperbolic cosine. It makes the hyperbola, the mass shell, the dispersion function, works out, and I do a little bit of funny algebra here, but just making a common denominator out of the thing. What I end with is sine hyperbolic minus cos, which gives me a minus sine. So what I end up with is a formula for the Lagrangian, which is minus the hyperbolic secant. And that's what it looks like. The hyperbolic secant looks like that. Remember from Lorentz contraction? There's that function right there. That's exact. That's an exact relativistic expression for this box of light, as far as its a phase behavior, you see, is. And the phase behavior is what got us started on all of this stuff. Now these are all those prior wave relations down there, either written in terms of the ordinary frequencies and wave numbers, and then the usual angular frequencies and wave vector that you can see. So just to compare the Lagrangian, which is this, and the Hamiltonian, which is this, okay, the hyperbolic cosine versus secant, okay, well, hyperbolic cosine is inverse to the hyperbolic secant, okay, and it's in fact equal to that. And then what you get is the cosine of sigma here is secant of sigma there. This includes the stellar angle in the mix. And so this is the geometry that we were talking about that has all of these quantities, and clicking on this will let us, you know, manipulate that like we've been manipulating other things here. So here is the Lagrangian secant written out just to second order. So it's minus mc squared. That means that you work off of the bottom of this circle, which is contacting the anti energy, the things whose phasors all go backwards, and then giving you whatever velocity you have, which gives you kinetic energy with a positive sign. This one up here, the hyperbolic cosine for low velocities, is giving you the positive mc squared plus the u squared. We already saw when we derived that. So that's making sense right there. And then, of course, there are these slopes, which give you the Lagrange equation, first Lagrange equation and the first Hamilton equation. The second of those are zero because we don't have any outside forces turned on yet. And then there's this whole thing where the tangent for this one comes down, marks off minus the Lagrangian as the value, okay, and that is the Lagrangian right there, the hyperbolic secant. And then it's on this curve right here, okay, the Lagrangian part of this thing right here also has a tangent, which marks off as an intercept the Hamiltonian, and you're back again. So around and round you go right there. Similar are the intercepts. These intercepts are also interesting for this. They're the phase velocity and the de Broglie wavelength. So there's a whole bunch of stuff all tied up into high school trigonometry, basically. Anyway, this is real quick here, just to compare the Lagrangian and the action, defining the Hamiltonian using the action. The action is the actual phase with an h-bar on it. Take the h-bar and put it on phase. You've got something called action. So that's the heart. You know, remember, when the derivative of that happens, it's the heartbeat of our matter. That's the differential version of that thing. Those are the Hamilton-Jacobi equations you get immediately from that differential if you assume that you want to integrate this thing closed form. And I think that's about it right there. Anyway, this stuff we already have seen. Now, this is kind of neat. This is where you actually make a transition between, say, a state up here and some other state that's maybe available down here. And here's a hyperbola for that state. Again, we're talking about a box of light or some sort of particle that has been made out of light. And the idea is that when you send out light, you've got to send out both the energy and then equal amounts of c times the momentum. Equal amounts of E, omega, and equal amounts of ck, or cp. So this axis right here has a c in front of its quantities, h bar k being p. So that's what happens. And the idea is that when I drop to here, I have to throw away the light that corresponds to that drop. So that's an emission process right there. And it has a Feynman diagram that goes with it. Basically, you're coming along at 0 speed, and you get kicked off that way as you throw out some light that has momentum of exactly that much. And there's your final state on this lower hyperbola when maybe you started on that point right there. So there's something that's very neat about the geometry of this. And that, first of all, is that this use of the waves, that is the fact that the waves are responsible, the phase wave is responsible for all the behavior, all the mechanical behavior, makes it so that the mystery of the conservation of momentum or the conservation of energy goes away. It's just the coherence of the waves. They maintain its constant wiggle. That's something that geometrically makes sense. And then the other thing are the recoil relations. In other words, how much did you recoil? Key recoil rate relation is this one right here. These two, the final omega L here, and I'm coming down from this point now for this particular example. So now I'm sending a photon off in that direction and dropping to yet a lower state. But whatever that is, the diagram that you see here is the one that we use to derive the relativistic transformations. It's just another example of working with geometry of hyperbolas. And it gives me this relationship between the two frequencies, the lowest frequency L and middle frequency M. Use a similar diagram for this one, similar equation for that one. And that boils down to a logarithm of, and you got to remember that each of these omega L's and omega M's are MC squareds divided by h bar, okay? Constants times the rest mass. When you do a ratio, those constants disappear. So you end up with a final velocity, the recoil velocity, equal to the speed of light, approximately. That's when rho is nearly equal to u over c. Otherwise, it's exact. But just an approximation for low recoil is this one. So you take the logarithm of what you, of the payload divided by the mass of the rocket with the payload before it blasted off. And that's indeed what this is. This is a rocket formula. V burnout is C exhaust, okay, logarithm initial over final. So I think this puts a squash to the idea of what we saw in that seminar by a guy from New Zealand. I can't think of his name right now, if you can think of it. But the idea, and I think he was interested in finding a squash to that. When he was, the idea is that a transition occurs infinitely fast. Well, at sub-relativistic speeds, when you aren't even counting recoil, I guess I can go along with that. But if you can really count the recoil, you can also measure time at this very fast rate of MC squares over h bar, right? So it looks infinitely fast. It looks sudden, but it isn't. It's very gradual. It's expelling this ethereal light or something, you see, and it's transferring mass. That's going somewhere, and it's going to give somebody a chance to get a little heavier, a little more massive, right? It has become less massive. That's what we're talking about here, is we're just measuring the rest mass, the phase frequency, right, the heartbeat, and we're counting those things, you see. So I think that's really important. It's also important is I can discretize this, so I can make a whole network of things to do what we haven't done yet, and that is really explore the Lorentz-Poincare group in detail as we make transitions, pretending that they're the only ones available, and then you can make it finer and finer and finer to improve the approximation to the real world, which seems to be maybe infinitely fine, but we don't know that. This is just pointing out that what we're really dealing with a box of light is a stack of hyperbolas, and that the transitions are first quantized and second quantized. First quantized is getting the modes in a box. That's what you do in elementary quantum mechanics with psi waves. This is electromagnetic waves, which are behaving like psi waves. And then the amplitude, the quantity of the thing, the quantized amplitude. Quantized means quantity. That's the second quantization, to make a oscillator functions out of the amplitude as your eigenstates. And then you mix those up to make coherent states. And you'd better do that, because otherwise we wouldn't have any of the coherence that led to any of this stuff. Now, this is a whole section here that has to do with taking this to the next extreme, and that is we've been putting two beams against each other, and in the process producing a frame, a Minkowski frame. So, you know, the 1200 coming into the 300 is what we worked with to make something that went at 3/5 the speed of light. Well, the idea here is that we're going to have a tunable laser, and we're going to chirp. We're going to chirp this one down while we chirp this one up, and we'll do it just right to make this point here go on some curve. Or, and this we can do analytically, make it go on a constant acceleration. What is that going to be? It turns out this can be a hyperbola, a constant g hyperbola. So we're going to actually make a coordinate frame that accounts for all of the time and space as I experience a very sophisticated set of Alice and Carla lasers building a manifold, which she's not going to provide us enough energy or momentum to actually get accelerated by that. But we're going to imagine we have the ability to follow it and just see what it's like, what's happening to the time and space that they're providing for us. So there's a blow-up of that right there. Well, the algebra, it turns out to be very simple. I find that the descriptions in Wheeler-Meisner and Thorne are a lot more complicated than this, but then they don't have the advantage of using waves to set things up. Light waves give a heck of a lot of sides to it. So there's that area that we call rho right there. It's half of it anyway. And we just study how that grows as they do their thing, which is provide so that this would be a constant acceleration. I would feel a constant acceleration at any point if I was following that curve. And from the looks of it, there'd be more acceleration for this one than it would be for this one and for this one. And that, again, depends on your viewpoint. So the picture of that is really quite amazing. So you have this manifold where you're talking about people down in this region. They're really tiny and very slow, or at least very low frequency. So this is something that still needs to be studied. It's I think there's a lot to it. It's something that shouldn't be bypassed. The Einstein elevator with constant acceleration is not trivial. And I think there's a lot of fun to it. This was an old way of looking at it, but now that we have much better graphics, here I can imagine that when Carl is accelerating just at this moment, he lets go of a monkey wrench or something, and that monkey wrench in this frame doesn't move, so as time goes it's just a straight line. But it doesn't look like a straight line to Bob here, who runs into something going half the speed of light at that point. And the distances right here are typically, if you make 1G, are typically a little less than a light year. So you're talking about enormous distances on these graphs. Okay, I think that's way over time. But that's about it for this course. And I hope that this crazy way to look at space and time is, something that's fruitful for you later on. Certainly the fourth kind of mass, gravitational mass, that's a whole question that needs to be looked at. If it, just an ordinary mask comes out with 3 kinds, I expect that there might be some funny business going on there. And you've got to get right with the waves. Let the waves tell you what they should do. Well, as they say at the end of any course, any questions? The answer is, yeah, I have a lot, but I can't phrase them.